Hey folks, we are back talking about a very specific situation called static equilibrium. I decided just to show a video of the an example problem of this to really talk and dig into what static equilibrium is, and how to go about it. So static equilibrium, it requires two main constraints. First off, the things involved don't accelerate. All right, there's no acceleration of the system. There's no acceleration. I mean, that's normal equilibrium. Is no acceleration. The thing that makes it static is that things not only don't accelerate, things don't move. All right, so we can't have any acceleration, and things don't move. And when we say things don't move, we mean linearly and rotationally, angularly. So the things to turn them into mathematical constraints, quantitative constraints, what we're saying is that the sum of the forces on these objects or this system, right, the sum of the forces needs to sum to zero. But we're also saying that the sum of the torques on this system also sum to zero. I cannot spin and I cannot translate. That's what we mean by static equilibrium. It's kind of that simple. But in practice, it requires us to do a little bit more than just a free body diagram like we've been doing for regular equilibrium. So let's shift over to our problem here. I have a 3-meter long ladder leaning against a frictionless wall at a 60-degree angle. What is the minimum value of the static coefficient of friction, μs, on the ground such that the ladder will not slip? So we have a really small diagram here, but it's working for us. I think it's important to now start to list the forces involved, and instead of just drawing a free body diagram, I would say let's start listing them on the actual picture, because now placement of those forces matter. First off, I would say, where is our center of mass? A ladder doesn't really have a weird distribution of mass, so I would say that the center of mass is probably in, around the center. Yeah, that's close, right? Right about there. So we'll label that Cm as the center of mass. I think if we were told that it was very heavy at the bottom, we would then have to recalculate or reconsider where the center of mass is. Now, we always put the weight of this object at the center of mass. That's the other convenient kind of use of the center of mass. Not only will it naturally rotate around its center of mass if you have a non-external, if you don't have an external pivot point, and you start to have these off-axis forces, but this is also where you're going to put mg, right? This is where mg goes. We're going to say it's right at the center of mass. Now, I have two contact points. Obviously, I'm going to have a normal force from the ground here. Let's call it Fn1. And I'm calling it Fn1 because there's also a contact force from this wall. We're going to call that Fn2. And then the last force we have is the frictional force, right? The static friction force from the ground on the ladder. So these are our forces. We have 4 in total. If we were to draw a free body diagram, would have us say I have mg pointing down, I have Fn1 pointing up, I have Fn2 pointing to the right, and then I have my static friction force pointing to the left. And so if I need to say that the sum of my forces in all directions is equal to 0, that means that Fn1 is equal to mg. That also means that Fn2 is equal to Fn1 times mu s if we're looking for the minimum, right? Now, of course, this is a threshold value. It's a threshold force, right? We're always considering that we have a static friction force equal to or less than this, right? We can accommodate anything up until this point. So, so this is kind of what we're building out now. The other thing that we can draw, the other diagram, I suppose, that you could draw is something where you're placing the forces actually on this object. I would say I have Fn1 here, I have Fn2 here, no, sorry, Fs here, I have mg here, and I have Fn2 here. And the reason I would like to do this, even though we kind of just did that on our picture, is it really starts to illustrate, okay, I have an R from my center of mass to this, or from all the way down here to up here, right? It allows me to kind of visualize in more simplistic terms what's going on. Now, since the sum of my torques is 0, I can actually, about any point, since this is a static equilibrium problem, I can actually pick my pivot point. And the reason I can pick the pivot point is because I don't pivot. I actually don't pivot around anything, so any pivot point is just as valid as any other pivot point. So generally speaking, a pivot point in these problems is made, this choice of a pivot point is made out of convenience more than anything physical. Some people like to always just put the pivot point at the center of mass. That's fine. That's fine. I like to try and put the pivot point where there is a collection of forces working on the same point. So I would put the pivot point right here, right? I would put the pivot point right here because if I put the pivot point here, that means R equals 0. And if R equals 0, these two forces don't actually apply any torques. So it actually just simplifies my problem. All right, that's why I like to choose the pivot point wherever there is a collection of forces in one location. So if I think about this, I really just have two torques now, right? And one of these torques is going to, let's label it red. This guy, Fn2, is going to spin me clockwise. Mg would spin me counterclockwise, right? If I'm pivoting around this point. And so really I have torque 1 plus torque 2, that has to equal 0. Let's say torque 1 is Fn2 times my radius all the way to it, right, which is this guy. It's the entire length of this. So I'll say it's 3 meters, right? Sine of the angle between them, and I like to use phi here, so I'll say phi 1. Well, phi 1, again, we need to extend our r vector. Phi, going back to black here, phi would be this angle, right? Phi would be this angle. And so I actually know that that's going to be 120 degrees. Yeah, that's going to be 120 degrees for us because this angle and this angle are the same. Let's keep moving. Let's keep moving here. I'll do blue maybe for this second torque, right? Plus torque 2. Torque 2 is going to have a length of 3 over 2, right? 3 meters over 2. That's this length from my pivot point. And again, if I'm going up like this angle is 30 degrees. 180 minus 30 is 150. it's a 150 degree angle here, right? So I have times mg sine of 150 degrees. Let's actually put in the 120 degrees over here. And so this is all equal to 0, right? This is all equal to 0. This is balancing my torques. It's a little bit messy, but it works. And I needed to do one more thing. We always say that counterclockwise is positive. That would be this one. And clockwise, this one is negative. So I need to make sure that I've included that in here. This is going to be positive. I need to include a negative sign in this, in that, and that should do it. Let me just double check something here. I want to make sure that I'm not doing something kind of silly. Yep. All right, that all works out. Perfect. All right. So now we have our torques. I could actually solve for Fn2, right? I could actually solve for Fn2 here. Fn2, right, has to be equal to, if I throw that on the other side, the 3 meters are going to cancel, and I'm left with mg sine of 150 degrees over 2 times sine of 120 degrees. So I could calculate that. I'm not going to at the moment. I like to keep things in symbols as long as I possibly can. Let's actually go back over to our forces. We solved our torques. Let's solve our forces. Right? We said that Fn1 was equal to mg. We also said that Fn2 was equal to Fn1 times mu s. So if now we start substituting in, we now have a expression for Fn2. We know that it's mg sine of 150 degrees divided by 2 sine of 120 degrees equal to mg, so our mg's and mg's are going to cancel, times mu s, right? This is convenient because we didn't have to actually plug in those numbers then, right? So sine is unitless, 2 is unitless, mu s is unitless. So this actually works out. Mu s is equal to sine of 150 degrees over 2 times 2 times sine of 120 degrees, and when you plug that in, I get 0.29. That is our minimum coefficient of static friction to make this thing not slip. And again, it's because we're working in static equilibrium conditions, right? Our forces need to balance, and our torques need to balance. And I've given us a crash course on how I like to deal with torques, right? I like to basically show what the net motion of this is going to be, and that actually depends on the pivot point. That really depends on the pivot point. And I chose the pivot point such that these two forces gave us no torque. Remember that torque is equal to, or the magnitude of torque at least, is equal to RF sine of phi. And so if R is 0, then torque is 0, right? So this is a way to make things a little bit more convenient for us, but that's static equilibrium in a nutshell. I'll see if I can put together another worked example. If nothing else, I know we have some homework problems on it, so we can try them out there. If you have any questions about this, come to an office hour or email me. Feel free to reach out, and I'll see you in the next one.